Hello again. In a previous segment we spoke about cantilevers and how they can be used to support loads and distribute loads. We framed our discussion then in terms of cantilevers as bridges and as support beams. There are actual biological reasons for studying this though, and that's because the principle of the cantilever is an important aspect of animals being able to hold themselves up. We can illustrate this quite nicely with my friend here, Twiggy. This is a skeleton of a cat, and you can see that Twiggy has a basic problem here. She has a head which is quite heavy, and it has to be supported, held up on the end of a rather long vertebral column through here. And in this model right here, you can see that Twiggy's head is held up by this little aluminum yoke here. Obviously, that's not an option for the living animal, and so we have to understand how it is that Twiggy does manage to hold her head up without the presence of external supports like this. Now, the cat uses, and lots of other animals for that matter, uses the principle of the cantilever to hold up her head. And we can illustrate this quite nicely with a little diagram right here. This is actually a photograph of a dog skeleton. It looks a lot like Twiggy here. They're both vertebrates, and so they both have the same kind of problem. And in the case of our dog right here, there's a load of the head right there, and gravity is pulling that down, like so. And the head is on the end of this long vertebral column over here, and the question is, how is it that the dog or our friend Twiggy managed to hold up their heads? Well, this is where the principle of the cantilever comes in. You'll remember when we discussed the basic principles behind the cantilever, that the idea there is to take a load and redistribute it through a structure so that it can be supported effectively by strong structures. This is what's happening in the case of the cantilever made up by the vertebral column. This is a vertebra from actually quite a large animal, a horse in fact, and this is one of the elements of the vertebral column. The nerve cord goes right there. This right here is called the neural spine, and this massive structure right here is called the centrum. Now, what the animal does to support its head with a cantilever is it takes loads that are distributed through the neural spines in tension and redirects them so that they become compression forces distributed through into the centrum of the vertebrae. Let's illustrate how that happens in the case of our dog model here. So we put the dog model up here, and we're now going to see how it is that the loads are distributed. What's missing in this skeletal reconstruction is a whole host of tendons and muscles that span between the different elements of the vertebrae. These are the neural spines of the dog right here, and these connect the vertebrae one from another. So in the case of the cantilever of the dog, you have tendons that run from the neural spine here down to the neural spines of adjacent vertebrae. So we'll just draw in one of those. That is a tendon that's going to be holding this part of the vertebrae up, and these are distributed along many of the other vertebrae. There are other tendons distributed along adjacent neural spines that also help distribute the load. And finally, there are a series of tendons that span between the neural spines in an X form that helps hold those together. Now, we're not quite done yet, but you can see at this point that how this starts looking very much like a cantilever that we described in a previous segment. But as I said, we're not done yet because the head of the dog can still fall off or droop. So there's an additional cantilever that goes from this large vertebra here that spans along the length of this large vertebra along the back of the head. And those two things together help hold up the head and redistribute the load from a tension load along through here, down through the centrum of the vertebrae in a compressive load, finally to the shoulders, and then down through the shoulders to the arms. And so this cantilever principle is operative in these vertebrates. It's a quite common mechanism for holding up quite odd structures and interesting structures that animals are capable of producing. Now, if we come along and look at Twiggy, we can also see how the cantilever principle operates as a cantilever bridge as well. Twiggy has an additional problem to having to hold up her head. She also has to hold up all the guts here that are hanging from the vertebral column. And this is where the principle of a cantilever bridge starts to be useful. We've already discussed how the cantilever helps hold up the head this way. But we see we have two supports for the body here. We have the pelvis down on this end and the shoulder blades on this end. And you have the principle of a cantilever bridge operating in this case as well. Just as we discussed in the case of the cantilever holding up the head, you have additional cables of tendons and muscles that spread this way. So this part is held up as a cantilever as well. Now the forequarters, the arm, this is like one of the pillars of a cantilever bridge. You have loads on both sides, and that redirects the loads by compression through the center of the vertebrae and then down through the forelimbs. The same thing operates down on this end over here. You have a cantilever system that operates from cables of tendons that distribute up through here. You have cables that distribute load along the length of this, and you have the same kind of phenomenon down here. This acts as a second support of a cantilever bridge, holding up this load over here and also holding up the load of the tail, which can actually be quite substantial and can play an important role in not only stability of the body during locomotion, but also aiding in the maneuverability of the body in case that's needed. Okay, so that's a very simple example of how principles of cantilever bridges and arches can be used to explain how it is that animals manage to hold themselves up with these rather claptrap systems of bones that typically sit inside them. Okay, well that's all for now, and we will see you in another segment. Goodbye, Tweety.